So today we'll talk about mapping, which is another way of saying compiling, but without talking about all of the kind of compiler infrastructure. So we'll talk about how, given a high-level piece of code, how can we map it down onto a machine learning accelerator, or even just a CPU or a GPU. And specifically, we'll talk about the different optimizations that we do to the code to make it work better on certain pieces of hardware. And these optimizations are what, or many of these optimizations, you will apply in A3 as well to kind of get your code running quickly on different targets. So just 1 second. Conference. Okay, this is better. So what are compilers, right? And so most compilers have kind of 3 distinct pieces. And this wouldn't be like, an in-depth dive into compilers or anything, but this is just kind of to have a rough idea on what compilers are if you don't already know. And the 3 pieces are, you have a front end. And usually that takes kind of your programming language and converts it to some other language. And, in a classical sense, that it would convert it to assembly. And then you would put that assembly on your device and it would run it. But that's no longer the case. Now it converts it to something called an intermediate representation. So it's a kind of assembly, or it's lower level certainly than kind of your C++ code, or definitely your PyTorch or Python code, or anything like that. But it's much easier to run optimizations on this intermediate representation. And so from a language like C++, we usually convert to an intermediate representation, something like LLVM. And LLVM-IR looks a lot like assembly. I think I may have a code snippet in the next slide, but it's much easier to do optimizations there. And this part of the compiler, once we convert into this IR, is called the middle end. Not to be confused with kind of middle ends in operating systems and stuff. This is just kind of the middle of the compiler, sometimes also referred to as the optimizer. So when you compile some C code and you do -0, -01, -03, that's where these optimizations happen to make your code faster. And so what are these optimizations? They're mainly code restructuring. So can I move pieces of code around without changing its functionality? Can I break a loop into 2 loops or fuse 2 loops together without changing the functionality? Can I change the indexing so that my data fits better into the cache, or I need to fetch fewer cache lines? So all of that stuff happens in the middle end. And then finally, there is something called the compiler backend, also referred to as kind of code generator or codegen. And this part, again, transforms the LLVM-IR into target-specific code. And now that becomes, it runs on a GPU, or it runs on a CPU, or it runs on something else, or an ARM processor, or something like that. And so many modern compilers can now target different backends. And that's part of the reason LLVM was created, actually, to have like a unified intermediate representation that can be used to target different backends. Yeah, any high level questions about this? Okay. So when we say machine learning compiler, this is a very active area of research, and you'll hear about TVM in the next class. But having that previous image in your head now, a machine learning focused compiler usually consumes a domain-specific language instead of C++, which is a general purpose computing language. Now this, it would take a domain-specific language here. So all of these frameworks, which are subsets of kind of the Python language, or use subsets of the Python language, they would be compiled using that domain-specific compiler. So it wouldn't be able to compile any code, but machine learning code only. That's what it would be focused on. And usually in machine learning compilers, you also have kind of 2 levels of intermediate representation. A nice thing is that from these frameworks, you get this coarse-grained computational graph. So this is like your deep neural network topology. It's like big coarse-grained blocks that are connected together in some way. So something like convolution or matrix multiplication or addition or something like that. And so there is this compute graph layer where we also do optimizations in it. So previously I said, we only optimize on this intermediate representation, which is a lower level representation. Here we can do optimizations both at the graph level and at the kind of IR or assembly level. So in this case, we go from this coarse-grained representation or computational graph down to, again, some more fine-grained representation. And they do more optimizations there, as I mentioned. And then finally, you have, again, different backends to be able to run on GPU, CPU, and a new hardware accelerator or something like that. And you'll notice that, LLVM here is considered a backend for this compiler, as opposed to in the previous image, I showed that it's in the middle end or in the optimizer. And that's mainly because, we're adding another level to the stack here, which is, the PyTorch level, which sits on top of C++. And we have this extra intermediate representation that they came up with called a computational graph where we do optimizations. So now their view of this LLVM is that it's now something in the backend, something that generates my code, basically. And all of the optimizations in LLVM are kind of abstracted away from a person working on an ML compiler, basically. Okay. So, so in this lecture, we'll talk about just how do we, take a deep neural network and map it onto hardware. And we'll talk a lot about those optimizations which happen on the computational graph and below as well. So, so what kind of things should we care about there? So we should care about which data flow to use. So many pieces of hardware can support different data flows. And what is a data flow? It's like when you have, a wait stationary data flow or an activation stationary or output stationary, which we took in the hardware lecture. We'll talk about different tiling. So what is my unit of computation and my unit of memory that I'm fetching every time I do a computation? We'll talk about vectorization or parallelization. If you have multiple compute units or different SIMD lanes or different cores, how do you utilize all of those cores together and bind operations to them? And finally, I'll give an overview of some on-chip memory management passes. So as we discussed in the hardware lecture as well, your on-chip memory is really important because you have really high bandwidth from it to your PEs or processing elements. And so managing that on-chip memory effectively can determine your application throughput. And in the first few slides, we'll just go with this very simple 1D convolution example. So in a 1D convolution, you have your input here, and you have a filter, and you sweep the filter across the input. And so if I want to write that as a loop, I could write it concisely using those two loops. So first, I'm going over the range of S, which is the filter size. And I'm going for each filter entry, I am going over all of the elements in my activation, so Q, and I'm multiplying it by that, and then adding it to a running sum, which depends on the Q, depends on the index of the input. So for every input, I'm accumulating a running sum for every filter, right? And so one question now is, which kind of data flow is this? So if you look at this code, is it wait stationary? Is it input stationary? Is it output stationary? What do you think? Wait stationary. Who agrees with that? A show of hands. Okay, half the class. Okay, so yeah, so it is wait stationary because my outer loop is iterating over the weights. So whatever is happening in here, the weight is still constant, right? So or it's not changing. The address is not changing. So if I'm plotting the filter, the input, and the output kind of across time, then first I fetch filter 0, input 0, and I'm writing to output 0. and then the weight or the filter stays the same, and then using the inner loop, I go to the next input, and then I write in the next output or at address 1, and I keep doing that until you kind of finish the iterations of the inner loop, and then you go to a new iteration of the outer loop where you go to filter number 1, and then you repeat the same thing, and then filter number 2, and then you repeat the same thing. So the filter here is what's stationary, and so this is weight stationary. And so a more common way of plotting this is actually kind of this space-time diagram, where on the x-axis here we're showing the cycle or time where I'm fetching a certain weight or an activation or changing the address of my output. And then on the y-axis we have the address of that element, whether it's weight, activation, or input. And so why is this useful? This is useful because it tells me a lot about my application, certainly in terms of memory. So for example, here we're increasing the address from 0 to 8, but then going back to 0 and going from 0 to 8 again and again and again. So I mean, what effect would this have on a CPU cache, for example? It depends on the cache line size. But if my cache line size is 4, for example, so every time this happens, I would need to evict the cache of that element, or it becomes stale, and then fetch a new one, and so on. So this is how you can thrash your cache really easily. The same is true here, right? So these patterns are usually not really good for caches, unless the whole thing can fit in the cache. Then you have no problem. Another thing is, you have these weights that don't change. So where should I store them? So I'm not talking about CPUs anymore, but if you have an explicitly managed internal memory, then part of your compiler has to say, where does this memory actually go? So here, is it a good fit for leaving off chip, fetching every time we need it? Or because, we're using it in many times in succession, should probably actually store it to your registers or to your memory elements that are closest to the compute and cache it there. And so these plots are quite interesting, and we'll start looking at them in throughout different optimizations as well. I'll pause for questions. Any questions at this point? Or super clear? Okay. Okay, so now one of the things that the compiler can do is that we can change the data flow through the compiler, because different data flows can achieve the same final result at different performance on different hardware, but the same final result. So if you have a pen and paper or something, and this is how I would write that 1D convolution, using this weight stationary data flow. How can I convert this to output stationary and input stationary? So if you just try it out on your laptop or on a notebook now, there's just 2 loops and 1 statement, 1 address calculation, and 1 array access. So how can I restructure this computation to do output stationary, or maybe easier to start with input stationary actually? So how did it feel like being a compiler? So that's that's what a compiler would do. It could change your data flow in that way. So restructuring loops. You talked about reordering loops. You talked about changing iteration variables, recomputing addresses, and so that's all of kind of all examples of things that a compiler would do. So yeah, so let's take a look at what the solution is. Yeah, so and so whenever you do a transformation, you need to make sure it's functionally equivalent, or the compiler will error out. And so yeah, so I guess in this case you can't really replace S with W, but you can replace Q because they're the same size. And then that would just mean changing the address calculation to depend on Q instead of W, or vice versa. But you wouldn't really need to, you couldn't really do that for S because it's a different size, at least not without if statements or something. So So it's like if, yeah, you could iterate over W and then compute the S, which is the filter address, and then you have an if statement. If S is greater than capital S, then or greater than or equal to capital S, then you should stop the loop, something like that. That would still be doable. Yeah, I couldn't think of a concrete scenario where that would be useful, but it could be, your hardware is constrained and can only take your input and output, as iteration variables. You could design hardware that does that, for example, and your filters are handled in a special way. So yeah, so the compiler can do these kind of transformations quite well. Things like loop reordering, again, without changing the functionality to fit the hardware a bit better. And the way the compiler knows that this works better is it's usually embedded in a heuristic. So compilers are not exact machines that give you always the best answer for a specific hardware, just because of the possibilities here are very large. Usually, I mean, in this simple example, there aren't too many possibilities, but in other examples, it could be much larger. And so sometimes we have explicit kind of, not simulators, but just models of what, the cache hit rate and the cache miss rate would be. Sometimes even models of energy consumption and things like that in the compiler heuristics. And sometimes, people who are building the compiler just use those to guide their heuristics. So we don't have explicit models in there, but we just, the people who wrote the compiler kind of transfer that knowledge into the code. So now, looking at these different space-time diagrams for different data flow choices, we can see that, for output stationary now, we see the references for the output become constant. And like I said, that can work better on different kinds of hardware. And I mentioned cache a few times and how things can fit better into the cache or whatever. But sometimes you actually need to do this. So maybe we designed a specific hardware accelerator where it only supports output stationary. So that means whatever code comes in, I need to convert it to that template or to that pattern to make it work. Okay. So we looked at this first point where, we're using the compiler to choose the data flow of our code. Next, we'll talk about two very important optimizations as well. They're kind of obvious that you need to do them, but they're really important as well. So tiling and vectorization. So what is tiling? So basically, tiling is choosing the size of your input or weights that you want to operate on. So maybe you have matrices that are 1K size on each dimension, but you only have 16 processing elements. So typically you choose a tile size that either fits your number of processing elements or is a function of your on-chip memory size. So let's talk about memory first. And practically speaking, when we're doing tiling, that just means we take one of the loops and we break it into two loops. And so here I'm showing this simple example again of the 1D convolution, but then we took the loop iterating over the output Q, and we broke it into two loops. So now we have an inner loop which has very few iterations. In fact, it iterates over the size of your tile. Let's call it Q0 here. And then we have an outer loop that iterates over the number of tiles. So we're still going over the whole output, but just using two loops instead of one. And the way to compute, Q back from those two iteration variables is just, like this. So we multiply the outer loop variable by the tile size and then add the inner loop variable. And so what did I gain here? Like, why could this be useful, right? So it's usually useful on the first order, just because, you have a memory hierarchy and you need to fetch that memory from your external DRAM, for example, onto different pieces of your on-chip memory hierarchy. And so what to put where is usually determined by those tile sizes. And so if you have this inner loop iterating over, Q0, then maybe, you choose Q0 so that everything fits in your registers, for example, close to the PEs. And then you know that you can allocate that memory there. And so you say, okay, so this tile, for this loop iteration, I'm going to just put it in the registers, or maybe it fits in the SRAM. And that's where you will put it. And so usually your levels of loops, the memory associated with each kind of iteration of one of those loops would fit in one level of your memory hierarchy. And usually the innermost loop is the one you care about. This is your tile size, and that's what fits in your kind of your memory closest to the PEs, which in this case I'm just calling registers. So that's kind of the first benefit of tiling. You will often also see tiling being called blocking. And that's the same thing. It's just different terminology. And so block, especially in GPU land, is often just used, actually in CPUs as well, we use blocks, is often just used to mean a tile. And speaking of terminology, in CUDA, you'll often hear thread block as well. And so that's kind of the number of threads or your thread iteration variables that are associated with one of your tiles. In OpenCL, which is kind of the alternative to CUDA, which runs on AMD GPUs, but also many other things, the thread block is often called work group. And in CUDA, it's called thread. OpenCL is called work item. But basically, this is kind of what a block or a tile is usually referred to in CPU and GPU land. Yeah, and so we have the tile. We are able to fetch the memory associated with each tile into a level of our memory hierarchy. And then now we also have another thing. So we don't just care about memory, we also care about compute. And so, so usually we also choose our smallest tile so that it corresponds to the number of SIMD lanes or the number of processing elements on our chip. And so, so what we're doing here is that we would take a memory tiled version and we would parallelize the innermost loop. So that happens in vectorizing or automatically parallelizing compilers. And I mean, the only difference between those two loops here, at least in terms of pseudocode, is that your innermost loop now becomes parallel. And so the first optimization, the tiling, allowed us to get the memory close to our PEs in the kind of the lowest, the smallest and the closest memory to my PEs. And then the second optimization just leverage, all of the available PEs and, multipliers and adders and stuff to be able to run all of these operations in parallel. So tiling and vectorization are kind of two essential parts of compilers, especially for machine learning, because that's how you get performance from it. Now you'll see some CPU code sometimes which uses AVX or SSE instructions explicitly. And that's when a person doesn't, they can't rely on the compiler to automatically parallelize the code for them, basically. So the compiler is unable to do it properly because it's full of heuristics and it's supposed to work for general code. It can detect these patterns often quite easily, and so Intel, for example, exposed an API for people to write this explicitly parallelized code themselves. So okay, so yeah, so now for our same code for a tiled and vectorized version, this is what the space-time diagrams would look like now. And so you see at each time instance, we're actually doing two things, or we're fetching, two inputs because we're doing operations on two elements at a time. And so if I ask you kind of what is the number of cores or the tile size here, then it would be B2. So right, because yeah, because at each time step, we're fetching two pieces of two elements from my memory for both the weights and the input, and so that's what we're operating on as well. So yeah, so tiling and vectorization, they always go together. The way I think about it is that one of them, which is tiling, is mainly done for the memory aspect of it. But to get performance, you always need to, do both memory and compute. So first I choose my tile size to fit in my memory, and I know that it will match my processing elements as well. And then vectorizing just, leverages or takes advantage of all of the parallel computational lanes that I have. So the number of PEs or the SIMD lanes or the number of cores on a GPU or something like that. Okay, and then one final thing, which is kind of necessary for many devices, is binding. So we also, we have all of these PEs or all of those cores on a piece of hardware. We still actually need to explicitly specify which PE will operate on which operation exactly. And so in the example where we have two PEs, the simplest case is just to bind a loop iteration, the loop iteration variables to our PE variables or our CUDA, or not CUDA, our core variables. So, or our thread indices, basically. So the easiest thing is to take this parallel for loop and say that my iteration variable is going to be my thread index as well. So there are often cases where they're not the same number, like you don't have the same number of cores as number of iterations in your loop. Obviously that can happen. And that's why we have this abstraction called a thread. That abstracts away exactly how many cores we have. So we can issue the same number of threads as we have loop iterations, and then they're scheduled onto the hardware as soon as cores become available. So binding, I think of it more as housekeeping. It's like, yeah, I just need to make sure I have, an index for every loop iteration for a thread to operate on that, and that's what we do here. Okay, any questions at this point? Not really, okay. So, yeah, so I mean, we talked about many of the important optimizations or necessary optimizations really to get performance out of something like matrix model or 1D convolution or 2D convolutions. We choose the data flow, we choose tiling, vectorization, tile size for memory, and vectorization to use all of the PEs. And then finally, we need to bind all of these loop iterations or computations to one of the PEs. And then there are now, there are other optimizations as well. And as I mentioned on slide 2 or 3, we kind of have two levels of optimization. One of them operates on this coarse level, graph. And what I'm showing here is actually the compiler that we used back at Intel for our deep learning accelerator. And here are some examples of the passes that we have there. So fusion is often something that runs early, where we combine operations together to get more parallelism out of the computations. We also have, what we call lowering and strength reduction passes, where we have more operations that can be specified in software than the operations that are available in hardware. So, for example, deconvolutions, we just can map them to normal convolutions. Even average pooling, we can map onto a convolution. And then we would only need to have one operation in hardware called convolution. We don't need a specific operation for all of these different variations of it. What else? Element-wise addition. I think we mapped it to bias addition or something like that. So these are called lowering or strength reduction operations. Basically going from a richer set of operations specified at the user level to a more restricted and hardware supported layers. Then we had kind of in the middle of our compiler, we had what we called an optimizer. And this was really focused on just the memory management. So how exactly to use our different levels of memory and how to make sure that we're keeping data on chip as much as possible. They'll show a few examples of those because that was actually the hardest part. That's where we invested kind of most of our time and effort. And then the rest of it is again like housekeeping, addressing, computing the right address to read from, shape propagation and constant propagation, just making sure constants translate into no ops and they are just folded into your computation and things like that. Okay, so I mean this is a very abstract view of our accelerator where we have an FPGA, we have an on-chip buffer, and we have external memory. And our goal is to keep memory on chip as much as possible. And so one of the passes that's related to memory is called allocation. So where exactly do we put data in this on-chip buffer? How do we handle the memory there? And usually when you're storing data to your off-chip memory, you just do it serially. So you look for the first address that has no memory allocated to it. You make sure that you have enough space, and then you allocate a buffer there. But in on-chip memory, it's a bit different because you don't actually have that much memory to play with. So what we do is that we usually had this, double buffered scheme where if you have a buffer A, for example, that you need to allocate, you would allocate it, from address 0. So assuming, this starts from address 0 going to the length of our buffer or the size of our buffer, we would allocate address A at the very beginning. And then when we have another tensor to allocate, we, in the incorrect version, we would allocate it right next to A. And that's what you would do in external memory. But what we do instead is that we put it at the end of the buffer. Can anyone think of why we would do that? Or why this would be useful? Yeah. Yeah, that's correct, Larry. So basically, once you free A, in the first instance, you actually now have a fragmented buffer, right? So so if you have a really big tensor to allocate now, you won't be able to do it in the first version, but you may be able to do it in the second one. So that's absolutely right. So we try to maximize the contiguous buffer space available for use by doing allocation this way. Okay. So another tightly related optimization is also scheduling. So if we have a subgraph that looks like this, then we also need to decide on the order on which we kind of go through these operations. And so we actually played around a lot with the heuristics and kind of iterating over a complex subgraph like this. And here I'm showing again, our on-chip buffer usage for two different kind of iteration order. So both scheduling and allocation are quite tightly coupled here. So this first tensor, I can allocate it at the end of the buffer, and then my second tensor, if I'm just going depth first, for example, then this is where I would allocate it and so on. But we found a heuristic where we kind of allocate the biggest buffers first. And that actually shrunk the size of our buffer by about 35%. And so, this is another example of, at the coarse-grained computational graph, we are not changing the functionality in any way. We're just changing the order in which we do those operations. But we're able to save about 30% of the on-chip memory buffer size. So yeah, so I mean, the analogy I like to give there is that, this is spatio-temporal Tetris. So we ended up formulating this into something called ILP, integer linear programming. And each of our buffers was a two-dimensional shape. And we just needed to make sure that they fit correctly with, in our, space-time diagram of our on-chip buffer without, having any data inconsistencies or data hazards or things like that. So, yeah, so I mean, we're almost at the end of the lecture. I see people are kind of already tired and dozing off, which is, yeah. But I have just a few more slides about, this concept of a mapping space. It's usually very large because you have all of these options. If we talk about binding alone, like thread binding, if we have 10 operations and we need to bind them to 10 different cores, there are many different ways of doing that. Many of them will be equivalent. So even though you have a really large mapping space, many of them are functionally identical, or even performance-wise, they wouldn't make any difference. And many of them are invalid. So many of them just would make your code not functional. And so, for example, if you choose a tile size that doesn't fit into memory, then that would just be invalid. So, as I said, we usually navigate the space using heuristics, and we usually build those device models to make sure that we can actually do it in a way that would minimize our objective. And I think it's important to also kind of have a mental view of what instructions look like, or low-level hardware instructions look like for deep learning accelerators specifically. So I'm not talking about CPUs or GPUs anymore. But because these pieces of hardware are so specific, you would usually find very specific ISAs as well, or instruction set architectures. So for example, here, we have the compiler doesn't even need to worry about the data flow of your matrix vector multiplication, because there is a low-level instruction that does that. So the compiler would just need to make sure that this instruction is called at the right time, and that's it. And so increasingly, these compilers for machine learning accelerators, something like a TPU, are becoming much simpler than than compilers for general languages like C++ or CUDA even, or something like that. You would often also see these very long instruction word instruction sets, where you have an instruction like convolution, but then it's followed by all of those hyperparameters, like the size of the filters, the padding, the stride, and so on. And this would actually be a low-level instruction in your hardware. So again, your compiler would just parameterize these coarse-grained operations and then send it to the hardware directly. And so I think the TPU has these kind of instructions as well, like do convolution or do matrix multiplication and so on. And sometimes the hardware doesn't have all of the instructions, like I said. So I've seen accelerators where they only support matrix vector multiplication or vector-vector multiplication. For example, the Grok TSP is like that. And so the compiler would then have to lower a convolution into different matrix vector multiplications, like we saw in the previous lecture for the image to call kind of algorithm. So the compiler would be in charge of that instead of a user writing it themselves. Yeah, and this is kind of, I think I'll end with this slide actually, but this is another example of kind of a coarse-grained optimization, which is increasingly, we're seeing more and more of those optimizations and fewer of the fine-grained optimizations actually in production deep learning compilers. And so what I'm showing here is, this is a res module. So this is one block of a ResNet neural network. And we have a 1x1 convolution, a 3x3 convolution, and then a 1x1 convolution added to another 1x1 convolution. So we have this kind of structure here. So one of the optimizations in our compiler is actually to reduce the number of operations and increase the parallelism. So to have fewer but bigger operations. And so instead of having two 1x1 convolutions that are added together, we can actually do a depth concatenation of those tensors and perform the whole thing in a 1x1 convolution. So we took those three operations and we basically fused them into one operation with a lot more parallelism, because we have a lot more elements to multiply here in every pass of this filter. And so these kinds of optimizations that expose parallelism are usually really good for DLAs that have a systolic array of 128 by 128, and that's the smallest block. Also for GPUs where you have all of these CUDA cores that would be sitting idle otherwise. And so you see a lot of those optimizations where we're coarsening the computational graph, like I'm showing here. So I won't go over this case study. It's in one of the readings that you're going to read. It's actually in both of the readings that you're going to read, two different versions of it, because I think we're basically out of time. Yeah, I really recommend going through chapter 6 in the book. And these two papers are kind of, actually one of them is a blog post because it had better diagrams than the paper that they published. And the other is a paper that we wrote back at Intel that talks a bit about our compiler. So I recommend going through them to kind of understand more what production compilers look like and what kind of operations they do. But yeah, that's it. I'll hang around here if people have questions or anything. Yeah, thanks.